What is a monoid? By the end of this episode, you will understand the two properties of monoids, and you'll be able to apply them in your systems. That's a big promise. Well, my name is Eric Normand, and I help people thrive with functional programming. So why are monoids important? Why even bring them up? That's a really good question. I know a lot of people talk about monads, and I think it's mostly because they want to know what they are, and they don't understand them, and they think there's some magic in Haskell about how I/O happens with monads. But that's another topic. This episode is about monoids, because I actually think monoids are more interesting and more applicable to helping us write better code, especially in a parallel or distributed code in a system that's got computation that has to spread out over different cores or different machines. So a monoid lets you break up a task into smaller tasks pretty much arbitrarily. Okay, so you don't have to spend a lot of computation figuring out how to break it up. So you break it up into small tasks, spread that out to different workers. So these are on different threads or in different machines. And then here's the key: the monoid lets you put them back together, put the answer back together. Okay, so what are the two properties of monoid? The two properties of a monoid. So first of all, it's an operation. A monoid is an operation. It's not a type or a kind of type. It's not a property of a certain class of values. It's a property of an operation over those values. So, for example, addition of numbers is a monoid. Multiplication of numbers is also a monoid. Okay? All right, so what are the two properties? That operation is associative. Okay, I have a whole episode on what is associative. But so I've explained it before, and I'll explain it briefly in a second. And then the other property is that that operation needs to have an identity value. I also have an episode on that. So you should look those up if this is confusing. But I'll go over a brief recap. So an associative operation is one that has two arguments, otherwise known as a binary operation. So addition has two arguments, right? It has A plus B. A and B are the two arguments. That's pretty clear, okay? So it's got to have two arguments. Now here's the other thing. It's got to take two values of the same type and return a value of that same type. So all three things, the two arguments and the return value, have the same type. So look at numbers. Takes two numbers, returns a number. That's addition, right? Multiplication is the same way. Takes two numbers, returns a number. Okay, it's not returning a string or something else, right? It's returning a number. So that's part of what makes it associative. The other thing is that the grouping, because you've got this, it's kind of like, I look at it like a triangle, like an upside down triangle. I've got an A and a B, and it gives me a C, right? And they're all the same type. Okay, so because I've got the A and the B at the top and the C at the point at the bottom, you can think of this associative operation as a combining operation. Like addition is a way of combining two values. It's not always combining. It's not always clear that that's a good way to think about it. Like in multiplication, are you really combining two numbers? But with addition, you definitely are, right? You're like combining two piles of rocks into one big pile of rocks. That's addition. That's where sort of the abstract operation of addition comes from, right? Is you just have piles of things and you put them together, and now you have a big pile. And so if you imagine I have three things to add. I have A, B, and C. And I want to add them up. I can add up A and B first, get a number, and then I add C to that number. So I use the same operation again. So I did a plus, A plus B. I get a number. Let's call it D. And then I take that D and I do D plus C. And now I get E. And that is my answer. You notice I'm trying to make it graphical here. I had A and B, and then those are in a triangle, and they lead down to the point D. And then that D and C form a new triangle, and it leads down to the point E. Okay? So that's one way I could do it. Or I could do this other way, which is I have A plus B plus C. I could take B plus C as the top of the triangle, go down to D, and then do A plus D and go down to E, right? So graphically, it's kind of symmetrical, right? It's the same. I'll get the same answer, but I've grouped them differently. The triangles kind of group on one side, they group to the left, and then on the other side, they group to the right. Okay, that is what associative means. Really, when you put this into the context of doing work over a distributed system, what it means is I can make like a hierarchy of workers, where the workers at the bottom of the hierarchy, the bottom of the tree, are adding up the tiny bits. And then there's like kind of their supervisor right above them is adding up all of the work that they're doing into a bigger number. And then there's the supervisors of the supervisors, and they're adding up all of the supervisors' work. And then there's the supervisor of the supervisors of the supervisors, and then they're adding up all their work. And then there's kind of like the supervisor up at the top adding up everything. So you can make a hierarchy, and it doesn't matter how they're grouped, right? That's what associative means. That the triangles, as they're added up, I guess this way the triangles are going up, but as they're added up, it doesn't matter how they're grouped. I can do the work at the bottom, and it will get grouped up into the top arbitrarily. Because it's what you don't want to do when you're distributing the work is spend a lot of time spending CPU power, figuring out, what's the best way to break this problem up. You just want something like, I'm just going to chop this pile of rocks in half with, just put my hands in it, just push it in roughly 2. You get 1/2, you get 1/2. Now start counting, right? And what they're going to do is they're going to say, it's too big for me to count. I'm going to split it roughly in 2. And I'm going to tell my, sub-supervisors to work on it. And then they're going to they're going to split it up into 2 and give it to their 2 workers. And then the answers will bubble up through this associative operation. Okay. Probably digress too much about associativity here. I do have a whole episode on it. The other thing is it needs an identity. This is in order to be considered a monoid, right? This is just the definition of monoid. So identity really means an empty value. Okay, well, let me put that in quotes. Empty value. In numbers for addition, the empty value is 0, right? It's kind of like, where do you start? So before you count, where do you stand? Where do you start? You start at 0. Then you start 1, 2, right? So you start at 0. You don't have to say it when you count because it's assumed I have 0 before I start. Okay. With multiplication, the identity is 1, which is where you start, right? Because if you started at 0, you multiply it out, you're always going to get a 0. So 1 is sort of like the null value, the value that doesn't change anything. That's what the identity means. Okay. So basically, you need a way for someone to get started. You need a value that they can start at. So your workers are saying, well, I haven't counted anything yet. I'm at 0. Right? Okay. Don't want to digress too much into identity. Again, there's an episode on that if you want to learn more about it. Okay, so let me give some examples of monoids in case this wasn't clear that it's not just about like addition. So string concatenation is a monoid. Okay, so if I have string A and string B, I concatenate them, I get a string C. Notice it's got the types are all the same. String, string, and string. Okay. And then it's got an identity. What is the identity of strings, of concatenation? It's the empty string. That's where you start. If I take an empty string and I concatenate it onto any string, I get that string back. Front or back. Same, likewise with list concatenation. Lists and strings are pretty similar structurally. Map merge is associative. If I take two maps and I make a new map that has all the keys from A and all the keys from B, that is associative. The identity, you can probably think of it, is the empty map, so no keys. That's perfectly fine. I've already talked about addition and multiplication. And and or are associative. They take two Booleans and return a Boolean. The identity is different for or. The identity is true, and for and the identity is false. Wait, is that right? No, I said that wrong. For or the identity is false, and for and the identity is true. Okay. You can work that one out for yourselves on some paper. I think it's a useful exercise. And then some other things you might not think of as monoids that are, if you squint, they're combining operations. Min and max. So min takes two numbers and will return the smaller of them. So again, remember we got the two types, the two arguments, same type, return value is the same type. Okay. Doesn't matter how you group it. If I have three numbers, A, B, and C, and I want to figure out what is the smallest of all three of these, I can take the first two and then and min them, and then the result of that and the third one I can min it. It doesn't matter how I start, how I group it. Okay. Same for max. And then so min is associative. What is its identity? Well, the identity of min has to have the property that if I do min with that identity and any other number, let's call it A. So the identity minned with A will always give me A. So what number is that? And when you think about it, it must be positive infinity. It must be the biggest possible number or some logical representation of that, of infinity. A number that is bigger than every other number. Likewise, the identity of max is the smallest possible number, which is negative infinity. Some logical representation of that. So that's great because that means that in a hierarchy, in a tree, you can figure out the biggest number or the smallest number. And there's actually a story that I've seen this in a video somewhere. I don't know where, but someone was trying to show that you can do work, a distributed work in people. And if each person does just a very small task, the whole room could come up with the correct result of the computation. And so what they did was they asked everyone to write down their birthday. And then when everyone had finished that, they were in rows. It was like a theater, right? like a theater style classroom. And they said everyone, if you're on the left, pass. So there's no one to your left. You're the furthest on the left. Pass your birth date to the right. And then if you have 2 birthdays in your hand, pass the biggest one to the right. Okay. And then, so the highest birthday in the row starts to bubble up to the right. Okay, because everyone's doing this one little comparison operation. They pass it to the right. So then the person on the right, so the person with no one to pass it to, they have 2. What they're supposed to do is pass the highest one forward. Okay, so then now you have the rows are bubbling up their the highest birthday to the front. And so the person in the front right position in the classroom, when everyone had passed, right? So everyone except for the people on the left, they now have 1 card, except for the person in the front who has 2. He has, you're right. He or she has 2 cards. Some card plus the highest one, which is the highest birthday. And so then the professor took the card and said, okay, this is the birthday of the oldest person in the room, and read off the birthday. And then that person stood up, and it was like some old person. And it's like, oh, it worked, right? There's the oldest person in the room. And then they asked, is anyone older than that? And it was no. So they found the answer. And when you think about this, they were doing the max operation on the dates, or maybe the min operation, because it's the oldest birthday. So it's the minimum birthday. They were doing min, and they were able to combine them first on a one-on-one basis. But then you notice the min of, so that's, each individual person was doing one comparison. But then when the min for the group was discovered, for the row was discovered, that one was minned with the whole class. All of the rows were minned together. And so this is an example of arbitrary grouping. So whatever rows happened to exist, it was arbitrarily grouped. And then arbitrary grouping of the rows. They were in some random arbitrary order as well. And so when the answer bubbled up, it was a single return value that had been the min of multiple mins. Okay, so that is the power of associativity right there. That you can start with 2 things, so 2 dates, compare them, you get an answer, and then someone else is doing the same thing. They're comparing 2 dates. They get an answer. And now you're comparing those 2. You get an answer. Right? So it's like a hierarchy, and the answer is bubbling up. Okay, so I think that's a pretty good story for explaining how these things can do distributed work and why they're so good at it. You could imagine having this classroom do lots of work like that. Lots of different kind of computation tasks, right? They could add up numbers where each person has 2 numbers, and then they pass the answer to the number to the end of the row, and they add up all these numbers, etc. And then the rows add up all their numbers, and the work is done faster because it's done in parallel. Each row is working at the same time. All the rows are working at the same time, instead of one person going through one number at a time, adding and adding and adding and adding. Right. So I just wanted to give one more example of a kind of task you would do. Let's say you needed to figure out let's say that you're at a school. Okay, it's just one building. It's got all these classrooms. And you need to figure out a lunch order for everyone in the whole school, because you're going to have lunch delivered today. And you know that if you went individually as one person to each person in the school, you could figure out the lunch order, but it would take longer than you have because it's already 9 a.m. You have to get everybody's order. Then there has to have time to cook it and deliver it for lunch. So there's just no time to walk to every person and ask them. So what can you do? Well, to break this problem up, you can say, well, if I have 2 lunch orders, I know how to combine them into a bigger lunch order. So if everyone writes down what they want, they're like, let's say their student ID and then what they want for lunch. And then, so everyone has that first initial piece of data, right? Now, then you can have, like, let's say someone at the end of the row in their classrooms combine all of those into a single bigger order, right? So that's a combining operation. And then someone at the front of the class would combine all of the rows together into a single one. And then they would run to the floor manager, and that floor manager would aggregate all of the classrooms on that floor together into a bigger lunch order. And then all of the people, all of the floors would, let's say, move either down or up. It doesn't matter. But let's say they all send their order down. And then there's like a school manager that adds up all of those orders into one big order. And then they send it off to the catering service. What you're doing is basically a Hashmap merge, right? So everybody's got a key and value. It's their student ID and then their lunch order. And you're doing a merge between first everyone in the row. Maybe as you move to the right, it gets aggregated up. And then as you move forward in the classroom, the rows get aggregated up into a classroom hash map. And then the classroom hash maps get merged together into a floor level hash map. And then the floors get merged down to the bottom floor into one big school-wide hash map. And that can happen very quickly because each of the floors is up, and each of the classrooms and each of the people in the classroom, each row, each person is working in parallel. And so, as you know, it's basically the amount of time it takes for each. So the school-wide lunch order is the answer. It just takes as long as, let's say it's 4 floors, the merging of 4 hash maps, plus however long one floor takes to generate the answer, right? Because the other 3 floors are happening in parallel. So it's a way of gaining some time by doing things in parallel. Okay, but it's basically the same thing. You're taking this problem, you're breaking it up, you're making sure that the types are the same on the 2 arguments and the return value. Okay, so the type is hash map of ID to order, right? And now you can merge them. You've turned it into a monoid, right? You could say, like, if you were going to do this in an imperative, like just loop through all the students way, you might never make the hash map for each individual student, right? Because you might just say, well, what's your student ID and what's your order? What's your student ID? What's your order? What's your student ID? What's your order? And so you never made that smaller type or that smaller hash map to make it of the same type. But by giving everyone the sort of instruction to make the small hash map, you've now turned it into a monoid, which allows for this distributed collection of an aggregation of the data into a single answer. So you're breaking up the big problem, into a lot of smaller problems. You're having the computers other computers do the small problems, and then you're combining the answers. Okay, I'll recap super quick. So a monoid is an operation like Hashmap merge that is associative and has an identity. Some examples: string concatenation, min, max, map merge, addition, multiplication. There's a bunch of others. I went over a story about how a room of people could calculate the oldest person in the room in a distributed way. I also talked about how you could calculate the lunch order of a really big school in less time than it would take to go to each person individually. And that was it. So I have a little takeaway that you could do. The way I like to think of it is this classroom. I think it's like this classroom that did this distributed calculation is actually a pretty good way of thinking of how you could distribute some work. So if you could come up with this operation that each individual person can do, and then the rows can do, and then the whole room can do, because the person on the right-hand side of the row can combine, then you've got a monoid, and you can distribute the work to the whole classroom. So think of how you would get classrooms to do the work. Some examples that you might think of is adding. So adding numbers together. Let's say you wanted to calculate so everyone has like some money in their pocket or in their purse or something. So you could figure out how much money is in the room right now. That's pretty cool. So you can add it all up. You figure out the youngest person, the oldest person. You could figure out this lunch order or some other operation like that is able to combine or figure out, maybe like think of it like a tennis tournament. You're trying to figure out who the best person is, right? So you take two people and you figure out the winner between those two, and so that winner becomes the return value, right? And so you can, as a hierarchy, you can figure out who is the best tennis player in this tournament and you don't have to play everybody against everybody. You're doing like a monadic operation to get up to the top. All right. I do want to tell you, if you want to see all the past episodes, and if in the future you want to see future episodes, they don't exist yet. That's why they're future. You can go to lispcast.com/podcast. There you'll find links to subscribe. You'll also find a page for each episode that includes the audio version, a video version, and a text transcript of what I'm saying here. You'll also find my email address and links to social media if you want to get in touch with me. I'd love to hear about the kinds of problems that you've found that you can solve in this classroom, and let me know about them, and we'll talk about it. We'll get into a nice deep discussion. All right. I can't say I'll see you next time. So until next time, I'm Eric Normand. See you later.